Okay, in this tutorial we will cover numerical integration and how that's done in EES. If you look in the help index, then you will see there's a number of options here for us. If I start typing integral, I'll see that there's integral equation based table, and I'm just going to do this top one here. And it kind of gives you a brief overview of all the different capabilities that EES has to integrate. Whenever you are integrating, you have the integral of something. The integrand is the function that you're integrating, and the variable name is what you're integrating with respect to. So you need to define that ahead of time, and then the function call will look something like this. And so you have the function there, the variable name, what you're integrating with respect to, and I need to put bounds on this. So I need a lower limit bound, a lower bound, and upper bound. Integrate from this to that, and step size. How many increments? What's the size of increment I want to go from my lower limit to my upper limit? And if I leave that out, then I trust EES. You see this next line down here. I'm trusting that EES knows how to handle that and give me an accurate enough result. But at the end of the day, this is numerical integration. It's not symbolic integration. And so we'll do a very brief example. We'll do x squared. So I can do this in 2 lines or 1 line. In the examples that you see in the EES help files, you'll see that they, well, let's first just go down here and just say that I'm going to say y is going to be the integral. My first input is going to be the function here, and so right now I'm just going to leave this. I'm going to integrate y prime. The p is for prime, and I'm going to integrate with respect to x. And let's go from 2 to 4, and let's come up here in a different line and say that y prime, the thing that we are integrating, is just x squared. And so my function is x squared. I can literally just run this code now, and I should get a result of 18.67. So this is what I defined after I integrate. My variable name here is y, so that's what this is. Y prime is going to 16. Why is it going to 16? Well, the bounds of my integration were from 2 to 4. If I substitute 4 into my function that I'm integrating, that x squared, 4 squared is 16. And so it's taking that value of the function and stepping. You don't see this stepping from in this case 4, which is 2 squared. You don't see it stepping from 4 to 16, but that's numerically exactly what it's doing. And so if I change the step here to be a step of 0.5, that's a very coarse step size. I'm going to have 2 to 2.5, 2.5 to 3, 3.3 to 3.5, and 3.5 to 4. And so let's see how accurate that is. And so I had 18.67 before. I'm a little off now, 18.75. The true answer to this is going to be 18 and 2/3. This is a visual representation of what I'm trying to do with this simple function. Again, my function is x squared. That's what this line is here. The integral of a function is just the area underneath the curve. And so if I do it from 2 to 4, I can do this by hand. This is 1/3 x cubed evaluated at the 2 bounds, and I get 56/3, or 18.67. And so what it's doing numerically is it's taking this curve and it's breaking it up into finite chunks in the x direction, evaluating that. If you go back to your numerical methods class, then you remember there's different methods to do numerical integration. If I want to do just pretend that all of those are a bunch of rectangles, and I just add up all the rectangles, and I'm finding the area under the curve. A more accurate way to do it is a trapezoid rule, and so I look at the 2 sides and then connect those with a line. And there's other methods too, but the fewer discretizations I impose on the bounds between my lower bound and my upper bound, then the less accurate it's going to be, and we see that in our EES file here. And so if I take this down and I change it by an order of magnitude, so instead of 4, I've got 40 elements, or 40 divisions, and now I'm back to where I was in terms of accuracy. For most of the equations that you do in this class, you're probably going to be able just to leave that off and EES is going to do just a fine job of choosing a step size such that you get an accurate result. Okay, and in the help files, sometimes you'll see a tick mark here. That's this tick mark. That is not the single quote mark. Single quote mark, if I did that, it's going to give me an error. It's saying that I need another quote mark to close that. This is the, I actually don't know the name of it, but it's on the same key typically as the tilde. To get the tilde, you would hit the shift button and then type that key. But if I do that here, and now this is going to give me an error because I defined this here as something, but I used a different parameter in the arguments to my integral function. And so I would need to do exactly the same thing here. And whether I call it yp like I did a minute ago, or whether it's y and this tick mark like they do in a lot of examples, it doesn't really matter. It's a variable name. And so don't get hung up on the fact that, okay, I better put a double prime here. It's easier when you have a large system of equations to do it that way, because then the tick mark's a reminder this is y prime, this is y double prime. But I literally could call this anything I want to, as long as I'm consistent down here, and I get the same result. And I could call this anything I want to here. The result of that is going to be my integral evaluation. And so the nomenclature is standard nomenclature you're going to use for any kind of variable manipulation, etc. Okay, hopefully that gives you some insight. And I could change the function here. I could just type the function in here. I find it easier to do it in two separate lines in case I make a mistake. I get the same. So in this case, I could just delete this line and do it all in one fell swoop, and I get 18.67 just like I did before. But a lot of times our equations are a little more complicated than something like this, and so I will leave this to. It doesn't matter what the function is, it'll evaluate it for me, and you can prove to yourself that this is what you would get if that really was your function that you're integrating from 2 to 4. And if I had different bounds and I go from 1 to 4, then I get a larger number because it's a bigger number under the curve there. Of course, I don't know if this is positive or negative. I think it's negative. So you have positive areas, negative areas, and if I reverse the bounds, I should get the exact same thing that I had. It should just be a negative number. And that's what I see here. So, okay, hopefully that gives you enough direction on the numerical integration. You can look at the help file, and it goes through. There's some other functionality in there that is helpful, especially in creating a table. This table here. And so if you go through some of the examples that you'll find in the EES help files, what this does is it shows you the step size, and it just creates a table for you and how much each of those increments was worth in terms of its area contribution to the total area. And so you can play around with that a little bit, but the main thing is that you understand how to use this function and how to interpret the results. All right, thank you.